Hello students. In this video we're going to solve 5 second order linear constant coefficient homogeneous differential equations. Alright, so I'm just going to call these second order differential equations because that's quite a mouthful. Now the assumption at the start of this video is that you already know how to solve these if you were to encounter one individually. This is more of a strategy session just to show you the 3 different cases that you'll encounter. So this is a summary of the content that you've been through up to this point. So if this is the first time you're seeing this solution technique, I recommend that you stop and you go back and you review these techniques individually. I have several videos outlining each of these specific cases. So with that caveat in place, let's get started. Okay, the first thing that I want to point out is that you see 5 differential equations here, but you might have caught that I mentioned only 3 cases. That is because there are only 3 cases. Problem 1 is the case of what we call distinct real roots for the characteristic equation. Problem 2 is a case where we have distinct complex roots for the characteristic equation. And problem number 3 is where we have repeated real roots for the characteristic equation. Problem 4 is just another case of what's happening in problem 1. You'll see that there are just 2 distinct real roots. And problem 5 is similar to problem 2 in that we will have 2 distinct complex roots to the characteristic equation. Okay, let's proceed. So I write the characteristic equation down. Notice that the exponent of the characteristic equation matches the order of the derivative. So the 2 matches the double prime, the 1 matches the single prime, and r to the 0 is what's happening here, and there's a 0th derivative, no derivative taking place here. So I write the characteristic equation down. In this case, it does factor. You can double check that. Minus 2 times 3 is minus 6. Minus 2r plus 3r is r, and then r squared. I solve these. Now be careful. Some students make a common mistake where they'll say the roots are minus 2 and 3. Be very careful. Don't be too hasty. Set r minus 2 equal to 0 and r plus 3 equal to 0. And then push the minus 2 over, and you get an r equals 2 and an r equals minus 3. So be very careful. Also, you should just quick do a sanity check your answers. Plug 2 into this quantity, this expression here, and you get 2 minus 2, that gives you 0. Plug minus 3 into here, you get minus 3 plus 3, you get 0. Now if you have 2 distinct real roots, you just put them into the form of your solution. Here are your exponentials, and that's the solution to this differential equation. That's case 1, where we have distinct real roots. Here, case 2, I write the characteristic equation down, again matching my exponents with the order of the derivatives. My characteristic equation is here, and here I mean it's a good idea to check the discriminant anyways, but the discriminant is the term that's under the square root in the quadratic equation. So if I take the b, which is 4, the a is 1, and the c is 13, and I plug them into this term here, you see that we get a minus 36, which is less than 0. That indicates that we're going to get complex roots. So I just use the quadratic formula to solve this quadratic equation. The minus 36, I just grab that from over here in this area. That b squared minus 4ac is what's under the radical. And then I take the 2 and I divide it into both of these, so I get minus 4 over 2 plus or minus. The square root of 36 is 6, and then there's a minus 1 that gets left in the radical, but you know that the square root of minus 1 is I, 6 divided by 2 is 3, and 4 divided by 2 is 2. And I bring the minus sign there. So these are my 2 distinct complex roots, minus 2 plus 3i, minus 2 minus 3i. They will always come in pairs like this. We call those conjugate pairs. The minus 2 is the real part, the 3 is the imaginary part, And so the form of our solution looks like this. We have an exponential e to the minus 2t, and then I take the 3 and I plug it into the cosine and the sine, and I put my arbitrary constants, and we're done with the problem. The sines and cosines come from Euler's formula, and again, if you haven't seen this before, I've explained this in a previous video. I recommend that you go back and watch that video. It's actually a series of 3 videos on verification of Euler's formula, an example of Euler's formula, and then I solve a differential equation like this one. Here's the third case. Here we have the characteristic equation, again matching up the exponents with the orders of the derivatives. But when I factor this one out, you see that we get the same thing here. We get r minus 6 times r minus 6. Some of you might write that as r minus 6 quantity squared. That means that r minus 6 is equal to 0, so r is equal to 6. That's a repeated root. That'll satisfy both of those linear expressions. So when we write our solution, yes, you might think, oh, is that just going to be c1 e to the 6x plus c2 e to the 6x? Not quite. We multiply this term by an x. And I give a verification of that in a previous video. Okay, now just to make clear, you might see this equation as a separate case from this one, but it's really not. If I write the characteristic equation, it's r squared plus 12r. Now the y prime gives us a 12r here because the exponent again matches the order of the derivative. I factor the r out, I get r is 0 and r is minus 12. And so, you could write your solution this way: y of t is equal to c1 e to the 0t plus c2 e to the minus 12t, and that would be in line with what we had up here. But no one's going to write e to the 0t. That is 0 times t is equal to 1, and e to the 0. 0 times t is equal to 0, and e to the 0 is equal to 1. So we have y of t is equal to c1 plus c2 e to the minus 12t. And then finally, this last case, be careful. This is r squared. The 2 matches the double prime. This is the 0th derivative, no derivative. So that's just a constant, r squared plus 25. The most common mistake I see is students put an r here, and they conflate these 2 cases, 4 and 5. So be careful not to do that. Watch the order of the derivatives and the exponents of your characteristic equation. Now, some of you might know this slick factoring here, r minus 5i, r plus 5i, because minus 5 times 5, of course, is minus 25, but I times I is I squared, and I squared is minus 1. So you get the plus 25. If not, you just can push the 25 over to the other side, take the square root, you get plus or minus, and this is why you get the plus or minus when you take square roots, because of the factoring here. And the square root of 25 is 5, but you have a minus 1 under the radical, so you get plus or minus 5i. That is a purely imaginary number. So the exponential that you saw in this previous case is going to be e to the 0t. And again, e to the 0t is just simply 1. So I'm just going to write the cosine of 5t here and the sine of 5t as my parts of my fundamental solutions. Okay, so just to recap, these are the problems 1 and problem 4 are the cases of distinct real roots. And you see with the solutions will just involve exponentials with the distinct real roots for the exponents. Then you have distinct complex roots. So again, the word distinct comes up again. Here we have a real part, so we get an e to the minus 2t. In number 5, we do not get a real part, so we put e to the 0t, which is simply 1. And then the third case is repeated real roots. So there's only 3 cases you have to concern yourself with, and you just calmly write down the characteristic equation, solve it, because it will be a quadratic equation, and then just consider your roots. Distinct real roots, you get this form of the solution. Distinct complex roots, you get this form of the solution. Remember to employ Euler's formula and write your solution in terms of cosines and sines. And then in the case of repeated real roots, remember to add this term here, x, to make these solutions what we call linearly independent. That means they're going to be independent of one another. You don't want to just put the same solution. Otherwise, why are you writing it twice? Right? Okay, good luck.